video will be made available, so you can contact me at tracy.gill@noaa.gov, and I will be happy to send you a copy or a link to it. And Katie may be posting this somewhere as well. People in the room, please sign in and silence your phone. And so today is the second in an 8-part climate series co-hosted by the U.S. Global Change Research Program and NOAA, coordinated by myself and Katie Reeves. I'm going to pass the ball to Katie Reeves now to tell you a little more about the series and to introduce our seminar title and our presenter. Katie?
Good afternoon, everyone. Thank you, Tracy, and thank all of you for joining us for the second installment of the Climate Science Special Report webinar series. As Tracy said, my name is Katie Reeves. I'm the Engagement and Communications Lead for the U.S. Global Change Research Program. A quick introduction for those of you who may have been unable to join us last week and who are unfamiliar with my program. The National Climate Assessment is a mandated product of the U.S. Global Change Research Program, which is composed of 13 federal agencies and departments in the federal government, and that includes NOAA. The Climate Science Special Report, which we will be focusing on throughout this 8-part series, represents Volume 1 of the 4th National Climate Assessment, or NCA4. This report assesses the science of climate change with a focus on the United States and serves as the foundation for Volume 2 of the assessment, scheduled for release later this year, which will look at climate-related impacts, risks, and adaptation across the United States. The Climate Science Special Report was released in November 2017, and you can read and download it at science2017.globalchange.gov. So today I'm pleased to introduce Tom Knutson, lead author on Chapter 3, Detection and Attribution of Climate Change, who will present on Detection and Attribution of Climate Change from the CSSR, a U.S. perspective. Mr. Knutson is a climate scientist with NOAA's Geophysical Fluid Dynamics Laboratory in Princeton. His research interests include hurricanes and climate change and, unsurprisingly, climate change detection and attribution. He's a fellow of the American Meteorological Society and currently serves as an associate editor for the Journal of Climate. In his capacity as chair of the World Meteorological Association's task team on tropical cyclones and climate change, he's leading the development of a new science assessment on that topic. And somehow he's still able to make time to be here with us. Thank you, Mr. Knutson, for joining us on today's NOAA Science Seminar. I'll turn it over to you.
Okay, thank you, Katie, and thanks everyone for joining today. I will be talking about detection and attribution of climate change from a United States perspective, which is, of course, resulting from the report that we put together. As mentioned, there are actually 8 different seminars that will be presented as part of this series, and this is the second one. So we had a nice overview last week from Catherine Hayhoe, and there'll be another overview at the end in late August. I'm going to drill down today in a particular...
Tom, I can't hear you.
Oh, hello? Hello? Did we lose me? You cannot hear me?
I didn't hear.
Okay, I get a lot of messages saying they can hear fine, so I'm not sure who cannot hear.
Because the volume went out when you started switching there. No?
I get a lot of messages saying I can hear fine, so
I can hear you now, thanks.
Okay, I'll just continue on. So this, I'll be taking a particular path through the report, which is looking at detection and attribution of climate change. And of course, I'll be just touching just briefly on some of these other elements like droughts and wildfire, things of that. These we covered in subsequent talks. So first I want to sort of motivate today's talk with why would we focus so much on detection and attribution. This is actually a new chapter that was included in the National Climate Assessment, at least in the Climate Science Special Report. So why detection and attribution? Well, say we observe some change in the climate system, and then a natural question to ask is whether this is a sign of anthropogenic climate change or just some bit of natural variability. And detection attribution is a formal way of trying to distinguish between these different possibilities, distinguishing natural variability from anthropogenically forced climate change. Another reason we're interested in detection attribution is that we present these projections of future climate change that we obtain from models. But the question is whether these models that we're using for these projections are actually reliable or not. So one way we can test that is to see if the models have reproduced changes we've seen over the past century, see whether they're consistent or not with past changes. So when we do find examples of detection and attribution where we already see a change going on in the data and models are consistent with that change, that gives us increased confidence in future projections of the particular type of change we're seeing. Another reason we're interested in detection attribution is that while we know that the climate system is warming globally, there's a very strong signal in global mean temperature, we're not really sure what all the other changes that we're seeing in the climate system, which of those are actually related to human-induced forcing and which are not. So in some sense, climate change is sort of evolving, it's sort of fuzzy. We're still fuzzy on some of the details now, but as the climate change progresses, these details will become more in focus. But detection and attribution is a means of trying to bring these sort of fuzzier details into focus and distinguish which changes are really caused by anthropogenic forcing or not. Now, there was a recent paper out by Lloyd and Oreskes looking at the issue of type 1 versus type 2 errors that we might make when we're making our judgments of how much confidence to put in different types of assessments. So a type 1 error is if we're claiming that something is the case, say we're claiming there's an anthropogenic influence, but there's not. If that's actually not true, then we've made a type 1 error. On the other hand, there's a type 2 error where if you're missing something that is actually the case, or you're understating an effect, say you're understating anthropogenic influence, that's another example of another type of error that one could make. So the question is, which of these types of errors is worse? Depending on your use of statistics, you can focus toward minimizing one or the other of these types of errors. Now, in the material I'm presenting, we're basically using this more conventional approach of preferentially avoiding the type 1 error, which is a fairly conservative, cautious approach where we're looking for robust evidence, we're evaluating statistical significance, let's say a p-value 0.05. We're trying to avoid overstating anthropogenic influence. Alternatively, we could have preferentially sought to avoid the type 2 error, to avoid overlooking some anthropogenic effect. We could use weaker criteria, for example. If we had used this approach, that would lead to more speculative attribution statements, which have a higher potential for false alarms. At least what I'm presenting today is really, from a type 1 error perspective, deciding which type of error is you want to avoid is more of a sort of a policy question, or it depends on your audience. But I'm just clarifying that for today's talk. In some future assessments, we may actually start to look more at this issue of reducing type 2 error. Now, the key findings in our chapter 3, which I'll go through very quickly, the first one is on global mean temperature, and this is basically in agreement with IPCC AR5 that it's extremely likely that more than half of global mean temperature increase since 1951 was caused by human influence on climate, and we have high confidence in this. Likely contributions of natural forcing and internal variability over that period are minor. The second key finding was that the science of event attribution is rapidly advancing through improved understanding of the mechanisms that produce the extreme events, and through marked progress in the development of methods that are used for event attribution. So hopefully these will become a little clearer as we go along. I'll start with some slides on global mean temperature to sort of set the overall framing. This is a picture of global mean temperature anomalies, the two panels. The one on the left, now the observations are the dark lines, green, black, and red. Those are in basic agreement showing this pronounced warming over the 21st century. And we have this orange shading. Those are climate models forced by all forcings, both anthropogenic and natural forcings. You see there's a range of warming shown by the climate models, and the average of that is this dark orange curve. So that the all forcing CMIP5 models are in very good agreement in their time evolution with global mean temperature. On the other hand, if you take away the anthropogenic forcings, so you're only including the natural forcings, you get this blue shading here in the right panel. And we see how the observations, all three data sets, are sticking out very sharply from this natural forcing. So this is an example really of detection and attribution. The detection is where the observations are becoming very distinct and outside the range of natural variability. So we say we detect a climate change. And the fact that the observations are falling inside the envelope and the set of models where we include the anthropogenic forcings then is an example of attribution, because this is showing consistency of observations with the models when we include the anthropogenic forcings. Now, global warming hiatus has received a lot of attention of the past several years, and I'm just kind of showing where it fits into the picture. It's basically this little kind of temporary pause in the warming here, which we see seems to have ended as we're now continuing to see this strong global warming signal. And we see that really this hiatus, this pause, was really just a relatively small event compared to the substantial overall warming, and appears to have ended. So there's not too much. I think you don't hear very much about global warming hiatus anymore in light of this. So from IPCC, they used more formal detection attribution techniques, which include pattern-based assessment, to estimate how much of this global mean warming signal that we've seen since 1951, how much of that warming is due to anthropogenic influence or other influences. So, and this, so to do that, they take a pattern from models. It could be greenhouse only forcing pattern or anthropogenic forcing pattern, and use that pattern to fit the observations and come up with some type of estimate of the projection of the model-based pattern on the observations. When you do that, see the observations here are showing this is in degrees Fahrenheit over a degree warming, and it's very close to the estimate that you get for the total anthropogenic forcing. So the anthropogenic forcing is essentially very close. That's saying essentially the best estimate is that all of the observed warming is due to anthropogenic forcing, which the anthropogenic forcing consists of a larger greenhouse force component offset by this other anthropogenic, which is a negative offset of aerosols, partially offset. But the net anthropogenic is very similar to observations. And we see the estimate of natural variability and internal variability contributions being relatively small, about 0.2 degrees Fahrenheit, so much smaller than the observed. That was one approach. There are other approaches. One can use linear regression of energy balance models. We showed an example of this in the report. This is where you're trying to break up this observed global mean temperature signal into its components by using multiple linear regression. We see the estimate of the solar contribution, the volcanic contribution here, and they're making just very minor contributions to the warming. By far, the largest contribution is anthropogenic component that we see down here, with again, natural variability is just showing more of just sort of wiggles along the way. That's consistent overall with IPCC's assessment. We looked at 2016 when global mean temperature set a new record. It set records in 2015 and 2016. So we looked at 2016 as an event and asked how likely it was that 2016's event could have occurred without anthropogenic forcing. And we find that, again, here's this 2016 sticking way out of this natural forcing ensemble. In fact, we conclude that you cannot simulate a warming, a global mean warming as strong as what we saw in 2016 if you don't include anthropogenic forcings. That statement is the case at least for the CMIP-5 models. So according to the CMIP-5 models, it is necessary to have anthropogenic forcing in order to have a warming as strong as what we experienced here in 2016. There's another way of looking at 2016's extreme global mean temperatures. This set of orange curves here are model estimates of internal climate variability, 24,000 years, in fact, of estimates from 36 models. And we see how far 2016's global temperature is sticking out of that envelope of this natural internal variability. So the models, if you're going to explain 2016's warming by some natural internal variability process, the models would have to be off by a substantial factor, more than a factor of 2, in order for that to be the case. Now, we can also look at global mean temperature just focusing on the period since 1970, as we do in this, as we do in this bottom plot. There, I've plotted these 12-month running means that show the El Nino events happening. So we see 1982, 83 El Nino event, 1997, 98 El Nino, the 2015, 2016 El Nino event. But these El Ninos, they're having a sort of a small bump in global mean temperature, but it's on top of this general rising trend we see here. So while the El Nino in 2015, 2016 contributed something to global mean temperature, it wasn't the cause, the dominant cause of this large sort of century scale warming that we see here in the plot above. In fact, we did try to quantify how much in this plot we're showing, and this is some work we published in BAMS after the Climate Science Special Report came out, trying to break down the 2015 and 2016 global mean temperature event into its components. If you try to explain it by natural variability alone, that would be these green bars are internal variability, and blue, the natural forced part. You could only get up to about 0.7 degrees, or here 0.9 degrees in the most conservative. I'm sorry, that's 0.7. In the most conservative case, you're not getting anywhere close, even in the most conservative estimates, you're not getting anywhere close to the warming that we've seen in 2015 and 2016. You need the anthropogenic contributions, these big red bars, to get into that range. And these are taking the largest event, the largest internal variable event that's even simulated in any of these models. Okay, so that was a little quick look at global temperature change, and we're very interested in the Climate Science Special Report about U.S. temperatures. So what could we say about U.S. temperatures? Our main conclusion was that detectable anthropogenic warming since 1901 has occurred over the western and northern regions of the contiguous United States, according to observations in CMIP-5 models with medium confidence. Although the southeastern United States, there's been no, over the southeastern U.S., there has been no detectable warming trend. So the combination of natural and anthropogenic forcings on temperature extremes has also been detected over large subregions of North America. Those were the headline conclusions. Now, looking at the data, this is a map of annual and winter and summer temperature anomalies over the U.S. comparing 1986 to 2016 time period versus the early 20th century climate. And we see strong warming over most of the U.S., but not over the southeast. There is still extensive warming, and it's stronger in winter than summer. We did a detection attribution study of this warming, which showing the 3 panels here, the results of that. So this is the observed trend. In this case, we're looking at the trend in surface temperature since 1901 in observations over the U.S. And this is what the models, this is the ensemble mean from the CMIP-5 models, saying what the models, if you force them with observed historical forcing, what type of trend you would expect from models. And now this is then, if we compare the models and the observations through the sort of summary assessment, we can see that in the green regions, we're basically concluding that this trend is not detectable there. It's not distinguishable from natural variability. That's in this eastern and southeastern part of the country. Over most of the contiguous U.S., large parts of the West and over the Northeast and the northern states, it is detectable, and in fact, it's also consistent with the CMIP-5 model. So we have detectable and attributable warming over most of the U.S. In terms of temperature extremes, this is some work from Min et al. In Journal of Climate. They looked at the trend since 1951 in different temperature extreme measures, the coldest trend in the coldest night temperature, the coldest day temperature, the warmest night temperature, and the warmest daytime temperatures. So you see the strongest signal, most consistent signals is for warmest nights. So the night times are getting warmer, that being the most consistent signal in over the U.S. in temperature extremes. And they then did a formal detection attribution analysis of that. And that's again where they use these pattern-based techniques and looking at model-based signals and computing a type of scaling factor between the model-based signal. So let's look at in the top curve here at the anthropogenic signals. So these are, this is where they're trying to see if they can detect an anthropogenic signal. And we have these, they did it globally, but I've drawn the box here over for the Western North America, Central North America, and Eastern North America regions. Now, when this red bar whisker plot, when it's above the 0 level, that's what we mean by detection. That means their coefficient, your coefficient, fitting coefficient is significantly different from 0. And we see that's the case for Western North America and Eastern North America, but not the case for Central North America. And this is for this, looking at the extremes, this warmest nighttime temperatures. Now the fitting factor is close and consistent with 1 also, which implies consistency of the models with observation. So it's saying there's moderately strong evidence then for detectable anthropogenic influence on extreme temperatures over the U.S. using this type of approach, particularly Western U.S., Eastern North America, Western North America. There have been other types of studies looking at extreme temperatures from a detection attribution viewpoint. We have studies which looked at different extreme temperature events, and this table is showing us a summary of a number of these which have come out, many of them in these BAMS Bulletin of the American Meteorological Society special issues on extremes. And these studies in general are finding, they're tending to find detectable human influence on a number of hot extreme events for various regions, various seasons, and so forth. So this is an example of this advancement that we've been seeing in the extreme event attribution. And again, extreme event attribution seems to be, the results seem to be most robust when we're looking at temperature-related events. Okay, so moving from temperature to precipitation now, here's what the report concluded about precipitation. For the continental United States, there's high confidence in the detection of extreme precipitation increases, while there's low confidence in attributing the extreme precipitation changes purely to anthropogenic forcing. There's stronger evidence for a human contribution, at least medium confidence, when we take into account process-based understanding, for example, increased water vapor in the warmer atmosphere. Also, the report concluded that mean precipitation trends identified for the U.S. have not been clearly attributed to anthropogenic forcing at this point. So I'll show some new results which maybe go a bit beyond that second statement in a few minutes. Okay, so this is a map of the trend or the change, long-term change in annual precipitation over the U.S. So this is comparing 1986 to 2015 average versus the early 20th century climatology. So we see a lot of green, so there's a lot of moistening, some drying here, particularly in the southwestern U.S. in the annual mean. And we see then some seasonal differences in the details of this type. But we're seeing a lot of precipitation increase, more increase than decrease, at least in the annual. This is an example of some new work done since the report came out, where we're actually trying to do more detection and attribution on precipitation signals. So to do that, this method that we're using is we're basically categorizing trends in precipitation as to whether they're detectable or attributable or consistent with models and so forth. And how do we do that? Well, this is a schematic showing, say, a distribution of trends from an all-forcing set of model calculations. So these would be models that include anthropogenic and natural forcing. And then say we have another set of model calculations which only include, say, natural forcings and don't include anthropogenic forcings. So then we can just see where the observed trend fits along this sort of spectrum here. If the observed trend is out beyond this 95th percentile of the natural forcing distribution out in this direction, we would say that's a detectable increase. And if the observed trend is also within the 5th to 95th percentile of the all-forcing distribution, then we would say it's both detectable and attributable to anthropogenic forcing, because the difference between the all-forcing and natural forcing is just the anthropogenic forcing. Now, if the trend we observed is way out here, so it's even much larger than the all-forcing, we'll still say it's a detectable increase and even attributable to some degree to anthropogenic forcing, but there is still some issue there because the trend in that case would be much stronger than models are saying it should be. And of course, if it's within the natural forcing distribution, we would say there's just no detectable trend. So if we use this type of scheme to categorize trends, first we could do it globally, and we've done so in this paper published in Journal of Climate. But let's focus in here on the U.S. So again, this is now we're looking at trends from 1901 to 2010 in precipitation, just focusing on the contiguous U.S. And blue are wetting trends, and brown are sort of drying trends. And this is the observed trend. Now over here we have the trend from the CMIT-5 models with all forcings. So we see there's some similarity between them, but also some differences. There's a lot of blue here in the Northeast and in the models, and much more blue than red, so much more wetting than drying in observations. So now, what do we do? How do these things compare then? How do we categorize these observed trends based on that schema that I just showed? Well, over these gray regions, we would say that there's no detectable trend, because we assess those trends as being not statistically different from natural variability only. Now there's a lot of blue here, especially over the Northeast and North Central U.S. That's where the wetting trend is very strong, it's detectable, and because it's dark blue, it's even stronger than the models are saying it should be. So we're seeing then detectable anthropogenic influence, and if anything, the wetting that we're seeing there is stronger than the models are suggesting it should be. Here, this green patch, that's saying where there's a detectable moistening trend, but the models are actually simulating a drying trend. So the models are sort of we're not consistent there. The models have the wrong sign in that region. So, but we do see a fairly large region here of detectable moistening trends. We don't see any evidence for detectable anthropogenic drying trends, according to this analysis. You can do the same thing from using trends from 1951 to 2010. You get rather similar results over the U.S. Again, some evidence of detectable anthropogenic moistening trends, especially over the north central U.S., parts of the northeastern U.S. And these light blue regions are where we have a detectable trend, which is also consistent with the models. And see some signs of still inconsistency here in the south central. And that result I was showing of the models not producing as strong a wetting trend as observed, you even see that even in the zonal average over the entire northern hemisphere. This black curve is these are the zonal average trends in observed precipitation over these northern mid-latitudes land regions, and the orange are all the different CMIT-5 models, and the red is the ensemble mean. So really the observations are at the edge of the model. So if anything, since 1901, we've been seeing a rather strong moistening trend compared to what we would expect from climate models. So I think it's an important thing feature to keep an eye on. Now, extreme precipitation is an example of something where we're seeing some fairly substantial changes over the U.S., and these are some figures from the report showing several different extreme precipitation metrics and the percent changes in these metrics. And the scheme is that yellowish regions are where we have decreasing, and then these other, from light green through blue, are where we have increases. So we see a preponderance of increasing trends, and it's especially strong here in the, say, the northeastern and eastern parts of the country. So we see increases in a variety of metrics, such as the maximum daily precipitation that occurs within 5-year periods, or the amount of precipitation that falls in these 99th percentile events, that's been going up, or the number of 2-day precipitation events that exceed sort of the 5-year return time event. All these different measures showing these increases over time. So, and another example is a time series showing the relative number of these 2-day precipitation events that exceed a 5-year return interval. This again over the contiguous U.S. from 1900, showing this increase over time in that precipitation extremes measure. So what about detection attribution? Those are just showing the observations. So there has been some work on this, on extreme precipitation. Zubin Zhang et al. Published this in Geophysical Research Letters. Again, global analysis, but we can focus in on NA, the North American region in particular, and they looked at daily precipitation and 5-day precipitation, again looking for evidence of anthropogenic signals using a formal detection attribution method. So we want to focus here on green, which would be the anthropogenic signal, and what evidence they find. So the green bar here is above 0, so they're finding detectable, and it's consistent with 1, so they're finding some evidence for detectable and attributable changes in extreme precipitation. For 5-day, the error bar extends down close to 0, so it's not quite as robust a result. But still, we're finding then evidence from detection attribution studies for anthropogenic contribution to these extreme precipitation increases. Here we're showing at least for North America, which is, and if you look at their data mask, is predominantly U.S. region. Okay, moving from precipitation to circulation and variability. So have there been changes in circulation associated with anthropogenic forcing? Well, here's the conclusion from Chapter 5. So the tropics have expanded poleward by about 70 to 200 miles in each hemisphere over the period 1979 to 2009, with an accompanying shift of the subtropical dry zones, mid-latitude jets, and storm tracks. We have medium to high confidence in this statement. Human activities have played a role in this change with medium confidence, although confidence is presently low regarding the magnitude of the human contribution relative to natural variability. So this was the main statement made in the report on circulation changes. and it's fairly cautious. So we're much more cautious about attributing circulation changes than we are, say, to some of the, particularly the temperature changes, where we have much stronger evidence of anthropogenic forcing. Chapter 8 in the report looked at droughts, floods, and wildfires. So Mike Werner will be presenting July 26th, OneNOAA seminar on this chapter. So I won't go into any detail here other than I can just mention that, I'll just mention these main conclusions that, first of all, for drought, while by some measures drought has actually decreased over much of the continental United States in association with long-term increases in precipitation, neither the precipitation increases nor inferred drought decreases have been confidently attributed to anthropogenic forcing. Actually, now with this new paper, we might be able to say a little more about attributing precipitation increases to anthropogenic forcing, more than we were able to say at the time of the report. Detectable changes. So there's been a mix of increases and decreases in some types of flood frequency over parts of the U.S. So we've seen there's been some detectable change, although attribution studies have not established a robust connection between increased riverine flooding and human-induced climate change. So the message there for flooding is some signs of detectable changes, which seem to be different from natural variability, but we can't really, we're having trouble pinning those changes on anthropogenic forcing based on, at least on the available studies that in the literature. And finally, there's medium confidence for a human-caused climate change contribution to increased forest fire activity in Alaska in recent decades, and low to medium confidence for detectable human climate change contribution in the western U.S. to wildfire. So Michael will pick up there, I'm sure, with it and go into much more detail on these with his seminar. Okay, turning now to extreme storms. The report concluded that there is broad agreement in the literature that human factors, that being greenhouse gases and aerosols, have had a measurable impact on observed oceanic and atmospheric variability in the North Atlantic, and there's medium confidence that this has contributed to the observed increase in Atlantic hurricanes since the 1970s. There's no consensus on the relative magnitude of human and natural influences on past changes in hurricane activity. So that was the overall conclusion. I'll go into some detail and also show some new results from some new studies relating to hurricanes here in the next several slides. So first of all, we can look at some of these major indices of Atlantic hurricane activity. So this is a multi-panel plot, but I want to focus your attention first on, say, this orange curve, which is U.S. landfalling hurricanes, and this is 5-year running mean going back to 1880 or so. And we see that there's been essentially no trend, if anything, like a slight, it's not significant, decline in the frequency of U.S. landfalling hurricanes. Now, if you look at the raw hurricane record in the Atlantic basin, basin-wide, there does seem to be an increase over time in hurricane frequency. That's this blue series here. But we find that if we don't actually regard this early pre-satellite part of the record as being reliable, because we think it's very likely that some storms were missed in the pre-satellite era. If you make some type of statistical adjustment for this lack of coverage in the pre-satellite era, so the pre-1965 era, we're estimating there were actually more storms, so there's probably, our best guess is that there's no significant trend even in basin-wide hurricane counts, at least after you adjust for observing practices. Now, there has been a trend in tropical Atlantic sea surface temperatures and global mean temperature, of course, and those are highly significant, but we're not seeing a similar feature here in U.S. landfall. And that's one reason why we make these relatively cautious statements in the report about hurricane activity for the U.S. Now, there has been this, if we go back here to hurricane counts, whether it's the raw counts or adjusted counts in the basin, there's been a large increase since 1970 or so. And so the question is, what has caused this increase? Is this being caused by anthropogenic warming? Well, it's not really reflective of the long-term change. So, however, there has been some work suggesting that there's a large multi-decadal variability in the Atlantic basin. This is showing it for sea surface temperatures, which, according to some authors, is being driven by anthropogenic aerosol forcing. But this is itself is up for debate, because an alternative view is that the aerosol forcing in these models is being overestimated, and that this is really just a reflection of a natural variability, the so-called Atlantic multi-decadal oscillation related to overturning circulation in the Atlantic. In any case, if it were true that that this this low level of sea surface temperatures and also relatively low level of hurricane activity, if it were true that that was driven by aerosols, then what we would be seeing then is some increase in activity, at least temporarily, as the aerosol loading over the Atlantic has decreased over time. But we wouldn't expect that to be to lead to any future long-term rising trend. That would be sort of a temporary thing. But again, this is still a matter of debate as to what has caused this multi-decadal variability. Here's something that has happened since the report. When we wrote the report, we were in the middle of a 11-year drought in U.S. major landfalling hurricanes, but 2017 season ended that drought. We had then two major landfalls over the continental U.S., which ended the so-called major hurricane drought, which, again, we interpreted that drought as most likely just being a temporary, some type of natural variability fluctuation. But this is, again, an update since the report. Now, looking at in the Eastern Pacific, this is an example of trying to do event attribution. So this is some work by Murakami and colleagues at GFDL, looking at hurricanes approaching Hawaii during the 2014 season. And there were 3 such storms in the 2014 season, and they noted that that was the 3rd largest number since 1949. And they also did some calculations, model calculations, looking where they tried to simulate the number of storms that approached Hawaii under different conditions. So we have the red bar here, that would be sort of pre-industrial conditions, and the green bar is their estimate for 1990 sort of control conditions, roughly speaking. And we see that the model they're using is simulating an increase in TC frequency near Hawaii, whether it be this is number 1 here means 1 storm approaching near Hawaii. Number 2 is the case where 2 storms approach near Hawaii. And again, you see a big increase when you add anthropogenic forcing in. Now, so that's indicating that anthropogenic forcing may have contributed to this relatively high occurrence of hurricanes near Hawaii in 2014. It's also important to note, though, that there's no real significant long-term trend in hurricanes approaching near Hawaii. So in this case, they're not really showing what we would call a detectable trend. So this would be an example of attribution without detection. So we don't yet see a detectable trend in the data. So in the case where you have an attribution without detection, you tend to have somewhat lower confidence in it, because the result is not being buttressed by occurrence of a significant trend. There's been this was alluded to in the report. This is looking at, again, another tropical cyclone metric, in this case looking at the western North Pacific, where the data are showing some poleward shift in the latitude of maximum intensity. This is some work led by Jim Cosson at NOAA's NCEI. Now, so this is the historical period here, showing this a historical poleward shift in that basin, which we see is just sort of barely meets statistically significant. What Jim has done, though, is regressed out the influence of sort of known modes of internal variability, namely the Pacific Decadal Oscillation, or PDO, and ENSO, El Nino Southern Oscillation. He regressed those out, and then he finds an even stronger trend than before after you take out their influence. So the PDO has maybe been suppressing the trend some, so he gets a stronger and much more significant trend here in the Northwest Pacific. And a poleward shift is what is expected in the future over this region, according to the CMET5 model. So we are seeing then some evidence for a detectable change, a detectable poleward shift in this region. We don't see such a shift in the Atlantic Basin, but we're talking about the western North Pacific. And the shift is in the direction that the models are projecting over the long term. So this is something that will be important to continue to monitor. The historical runs for this, by the way, with the CMET5 models also show a positive change, but it's not statistically significant. So one has to look at the future runs to see a significant change. So there are still some, in other words, this is not a completely robust example of detection attribution. Now, very recently, Jim Costin again published in Nature an analysis showing a global slowdown in tropical cyclone propagation speed since 1949. And he calculated that this slowdown amounted to about 20% over land regions affected by the North Atlantic tropical cyclones. So basically these regions here shown by the dots. So here's the time series of this translation speed. Again, since 1949, we have two curves here. One is the dashed line is over water, and the solid line is over land, where as you see from the trend here, the signal is stronger over land. So he finds this to be a significant linear trend. Although he comments in the paper, this is not an example of a detection attribution study, because it's still, this is a relatively short period, and there are lots of factors that potentially could be affecting, causing such a change. And from our own work, we don't see very strong evidence for changes in propagation speed of storms in our future climate projections. So in any case, this is a very interesting result and something that has come out since the Climate Science Special Report, but it could have important implications. For example, if storms slow down their translation speed, then they will drop more precipitation over particular regions. So that could be something that could enhance precipitation accumulations in particular regions from storms. So again, new results, something to keep an eye on, and something in need of further study. And again, as I mentioned, the 2017 season happened since the report, and the 2017 Atlantic hurricane season was a very damaging one. By some estimates, over 300 billion in damages. There were 10 hurricanes in a row, and we had the highest ACE values in the Atlantic since 2005. 4 Category 4 and 5 hurricanes. So it was quite an active season. And one of the most damaging storms in the 2017 season was Hurricane Harvey, which hit the Houston area with tremendous rainfall totals. It basically stalled out or propagated only very slowly after it arrived in the East Texas area, and had rainfall totals 60 inches or more that were measured. So, and it caused extensive damage, economic damages. So the question then is whether Harvey had any link to anthropogenic climate change. So, and there have been 3 or 4 studies out looking at this issue, and I'll show some results from some of these studies. This is from a study by Van Oldenburg et al. That, again, showing first of all, showing the precipitation accumulations over the East Texas region from Hurricane Harvey using different data sets. We see these very strong accumulations in eastern Texas. Now, they did a analysis of 85 stations there in eastern Texas along the Gulf Coast here, and looked at the occurrence of precipitation extremes in general. And this is a plot showing the precipitation extremes plotted against a smooth estimate of global mean temperature. So over here, where we have warmer global mean temperatures, here are cooler global mean temperatures. And then they fit the extremes using a generalized extreme value fitting. And they're able to create time-dependent fits, fits appropriate to the situation for 1900, year 1900, and for 2017, and then plotted these return periods for different classes of precipitation events. And you see the red curve here for 2017 is considerably elevated over the estimate for 1900. So it's saying there's been a secular change, increase in the extreme rainfall that one gets. Say if you're looking at the 100-year event here, the extreme rainfall has gone up. They did the same calculation for models. So they used 2 different climate models and looked at the extreme precipitation in this eastern Texas region for different conditions approximating pre-industrial and 2017 conditions. And they saw a similar kind of behavior where when you add in the anthropogenic forcing, you get a shifting up of these return period curves, implying more extreme precipitation intensities for a given return period, or conversely, if you're looking at particular extreme precipitation level, the return period of that level has been decreasing, so they've been coming more frequently. So they find that, according to this estimate, that global warming made Harvey's precipitation, or extreme precipitation in general, really, 8 to 19% more intense and 1.5 to 5 times as likely to occur. So they had several estimates. They had the estimates from observations, and from the 2 models, they sort of average them all together to get these estimates of changes in the intensity and changes in the probability of occurrence here. There was another paper by Risser and Werner, again looking at extreme precipitation in this region. So note that these are focusing not on hurricanes per se, but are focusing on extreme precipitation in general. And again, what they were finding is consistent with Van Oldenburg et al. They're finding some apparent increasing tendency in precipitation extremes, whether you consider a small region or a larger region in the area. And they did a time-dependent fitting of extreme values. So there's, again, another extreme value statistical analysis. And they did the fitting using the log of CO2 and the El Nino index as covariates. Using that approach, they showed this time dependence of the return period. When they looked at, say, the return period of a 300 millimeter event for a 7-day total, they show that return period is going down. So that means these extreme events are getting more frequent. And by the way, the Hurricane Harvey doesn't even show up on this plot. It would be about 700 millimeters, so it's off the charts here. But if they looked at the return period for a Hurricane Harvey type event, again, their analysis is showing that return period decreasing over time. That's becoming, the chances of such an event are being increasing over time. So according to their calculation, anthropogenic climate change, as modeled by this log of CO2, has likely increased rain amounts by at least 19%, with the best estimate of 38%, and likely increased the chances of such an extreme event by about a factor of 10 for best estimate, or at least a factor lower estimate of 3.5. So again, showing evidence for some human influence on these precipitation extremes. Gary Emanuel, the third of these studies, he tried to actually simulate hurricane events using an idealized hurricane simulation framework. And he simulated 3,700 events for that East Texas region. And he was looking for cases of 500 millimeter rainfall events in Texas. And he did it for both, he's showing results here for, say, the sort of current climate, and then, current climate here, or not current, but from the 1990 era climate versus late 21st century climate. And you see this red curve shifting down, so the return period for storms of a given magnitude has gotten shorter, and also the at a given return period, the intensity that one can expect has gotten greater. So he estimates the 500 millimeter rainfall event in Texas would be about 6 times more likely, just going from the year 2000 to 2017. So he estimates that as, he's saying that this is rapidly increasing. One thing to keep in mind is that Carey's hurricane prediction model is a bit unusual compared to other models used to do hurricane projections, in that it shows a somewhat more aggressive future tendency, for example, an increase in global frequency over the 21st century, whereas a lot of other models are not showing that. So there is some question as to how representative this is compared to what one would get with other modeling approaches. But nonetheless, this is suggesting that anthropogenic forcing may have played a role even in the occurrence of strongly precipitating hurricane events in the Texas region. Okay, that will conclude for the hurricane issue. Arctic changes are covered in Chapter 11 of the report, and Patrick Taylor will be presenting on August 16th. So I won't say anything more than just the conclusion that it's very likely that human activities have contributed to the observed Arctic surface temperature warming, sea ice loss, glacier mass loss, and northern hemisphere snow extent decline with high confidence. So see Patrick's talk for more information on these Arctic changes. Sea level rise, there was a chapter in the report on sea level rise, and Billy Sweet will be covering sea level rise, which was chapter 12 of the report, on August 23rd. So you want to tune into his. I'll mention the main conclusion here from a detection attribution standpoint, that human-caused climate change has made a substantial contribution to global mean sea level rise since 1900 with high confidence, contributing to a rate of rise that is greater than during any preceding century in at least 2,800 years with medium confidence. So we see, I'm sure Billy will go into more detail on these issues, but we see this reconstruction of historical global mean sea level from the report going back 2,500 years or so, and we see it has varied over time, but we see this rapid increase here in the latter part of the record and going to these unprecedented values here that they're talking about. And so while there has been variability of sea level on these sort of millennial and 100-year timescales, we see how unusual the most recent period has been. So again, see Billy's talk on August 23rd for more on sea level rise. There was Chapter 10, land cover, Chapter 13, ocean changes, I won't go into here. I see we've run out of time, so I'm just going to put the summary key points here, and then can take, I'll just leave the summary slide up, and then can take any questions that you might have. I think there have been some showing up in the chat window. So thanks very much for listening, and now I'd be happy to answer your questions.
Okay, great. Tom, can you see your chat?
Let me try to, I cannot, but let me.
Items to you if you like.
Let me see if I escape out of my presentation, I think I can pull up the chat. So
Right,
I'm going to do that.
Little bar that you have.
Let me see if I can chat. Is there a chat? Chat. Oh.
There's that little window that.
Okay. Yes. Yeah. So now I see some. Yeah. So I see a question. I'm sorry.
Oh, after I say I can hear you now on the chat, their questions began with Richard Heim.
Oh, so I guess I need to move somewhere in this chat window.
Just scroll up or down.
All right, let's see if we can scroll up. So, okay, the questions begin with Richard Heim. Okay. Richard Heim's question, why not do both? Analysis avoiding type 2 errors and analysis avoiding type 1 errors, then comparing the two results? That's a good question. For a new assessment that we're doing for tropical cyclones, we are going to try to bring in the type 2 error avoidance approach. Now, again, with the type 2 error, what we're trying to do is avoid making any mistakes, avoid missing any anthropogenic influence. So there's a trivial way of doing that, which is to say that any change you see, you can just blame on anthropogenic. But that's not very informative. We want to at least be able to say, to identify cases where we're confident that the expected force signal is in the right direction to explain some type of event. And also in terms of whether we're finding a detectable signal or not, what we're planning to do is lower the threshold and say, let's just look at it for a balance of evidence. In the case of trying to avoid a type 2 error, let's just look for a balance of evidence. Is there a balance of evidence that the change we're seeing is outside the range of natural variability? Is there a balance of evidence that it's that there's anthropogenic forcing has contributed in a certain way to that? So that's what that is what we're planning to do. But we did not do that for the again, the climate science special report was basically using the type 1 error avoidance approach. But this is I think an important point and one where policymakers, for example, can weigh in and tell us what type of error they would like us to focus on avoiding, or if they want us to present both, etc. So let me move on to the another question. Hopefully that's answered that. Michaela, is there a suspected reason that the southeast United States has not had a detectable warming trend, but other parts of the U.S. have? Okay, that's a very good question. We had a workshop looking at the southeastern U.S. here, and its various changes in atmospheric chemistry and climate here a couple of years ago at GFDL. And in that workshop, this issue was discussed quite a bit. There are a couple of possibilities. One is natural variability, that there's some type of multi-decadal signal which is sort of counteracting the warming, at least over the southeastern U.S. And so that would be some kind of temporary signal. Another, or a temporary delay in warming there. Another is that perhaps aerosol forcings are particularly contributing particularly strongly to cooling over the southeastern U.S. I think it's still an open question. I think more work needs to be done in that area. All we can say at this point is that the net result of whatever is happening there, we're not yet seeing what I would call a robustly detectable signal. You can find some evidence for detection even in the southeast if you choose certain types of time periods, but the reason I say it's not very robust is that for other types of time periods, for example, if you go back to 1901, we're not yet seeing a detectable signal there. But it's still a very interesting question and one we are continuing to look into. Let me move on to another question here. I thought there was a question from Hunter Cutting. Why do you prioritize avoiding type 1 errors over type 2 error? That seems to be a policy preference. You described avoiding type 1 errors as more cautious. In what way is that more cautious? Risk management calls for avoiding type 2 error whenever the stakes are large. In this light, the preference to be cautious calls for avoiding type 2 errors. And I think what Hunter is getting at here, which I think was also alluded to, I would refer the people listening to this Lloyd and Oreskes paper, which came out in just this year, that goes into this in quite a bit of detail. So type 1 error is avoiding sort of overstating an anthropogenic effect has been, I think, a more conventional approach. But we recognize that there are some audiences, or for some situations and so forth, where they would prefer to avoid the type 2 error. And I think we are planning to try to include this type 2 error perspective in an upcoming assessment on tropical cyclones. I'm not sure how much it's going to be picked up in other types of assessments. This is sort of a new sort of debate that's been brought in. But I agree with the questioner that there will be some for whom avoiding the type 2 error is the more important one. So we have to be careful that we develop these assessments so that we suit the needs of different audiences. I think there's also an audience for which avoiding type 1 error is the most important consideration. So I don't think there's really a one right answer. It really depends on the audience, or as one says, as Hunter says, a policy preference. So policymakers can tell us when they request an assessment report, they could give us guidance about which type of error they would like to see a preference given to in avoiding the type 1 error or type 2 error. Let's see if I can go on to another question here. Okay, Hunter Cutting. A frequency analysis published in BAMS established that the arbitrary choice of metrics is solely responsible for the illusion of a drought in landfalling hurricanes. Yeah. Moreover, Hurricane Sandy was the strongest storm on record to make landfall north of Cape Hatteras. In this context, why do you use the term drought to discuss the frequency of hurricane landfalls? I agree that the BAMS paper was, I think, important in showing how arbitrary that particular metric was. So my point in showing the figure is to show that even if you accept the metric as something useful to look for, that whatever temporary change there was, or temporary lack of major hurricane landfalls there was, it ran an 11-year period, and then that was it. I think Hurricane Sandy wasn't classified as a major hurricane on landfall, so it wasn't really included in that particular metric. So yet it was a very, very damaging storm because of its size and huge storm surge. So I think that's pointing toward the limitation of viewing hurricane risk from this sort of limited lens of just hurricane category or intensity, that one has to consider also the size and its surge damage potential and so forth. So that's just another reason why we have to be careful not to put too much weight on something like a major hurricane drought index. But nonetheless, there are all types of indices one can use to monitor hurricane activity, and that was an example of one which had caught the attention, I think, of the public and so forth, just because there hadn't been any landfalling hurricanes of at least Category 3 in the U.S. for a while, and people were wondering, well, why is that? So what I was presenting is just an update showing that that 11-year period without such landfalls is now over. Chris Lancy, okay, excellent talk. Thank you, Chris. With regards to trends and attribution, surface temperature is complex due to many issues: urbanization, station location changes, instrumentation changes, sampling considerations, etc. How does satellite-based lower tropospheric trends and attribution compare versus what you've shown? Yes, first of all, the satellite record is much shorter, so it's going to be harder to sort of distinguish anthropogenic influence from natural variability just because the length of the record is shorter. But I don't believe there is, and there's a whole field that's been looking at this satellite-based temperature record, and but I think the essence of it is that they're no longer finding any fundamental inconsistency between the satellite-based record and the land-based record. But of course, you mentioned the problems with the surface temperature, such as urbanization and so forth. Urbanization, I don't really consider to be much issue for global mean temperature, because the dominant signal is coming from ocean regions anyway, which are consistent with the land record. So I think that what the thermometer-based record, both over land and ocean, gives us is a way of looking at temperatures over broad regions, broad representative regions of the globe, in a way where we can reliably reconstruct a good estimate of the global average temperature anomaly. You don't need a huge number of independent stations to get a good estimate of the global mean temperature anomaly. Yet we have this very extensive record, which has been carefully quality controlled, and also shows this very substantial, very clear warming trend since the late 1800s, which I think the length of that record is really important, because it goes well beyond these sort of shorter multi-decadal periods, which can cause a little confusion. Say if one focuses in on temperatures since 1998 or something, I think one is really missing the forest for the trees. You have to really look at the full global temperature record going all the way back 1900 and prior to really see the strength of this warming signal that has us so convinced that there is in fact an anthropogenic warming signal now in global mean temperature. I think satellites have the advantage of full spatial coverage and so forth, but this very limited time history compared to just the thermometer-based records. And I think satellites have something to offer, and we should continue to compare the satellite-based approaches versus the thermometer-based record. But I don't think there's anything that we're seeing in the satellite-based record that would cause us to question the basic conclusions of this report about a very strong evidence for human contribution to global temperature increase.
Tom?
Yes.
You have a few more questions. Do you have enough time to take a few more questions, or do you want to take one more and call it a day? It's up to you.
I'll keep going for now. That's fine. So I see
Okay, and if you
one
could stay close to the mic, that would be great.
Stay closer to the mic. Okay. Sarah
Yes,
Green. Sarah Green asks, how many of the cases of non or weakly attributable results are due to data issues, not enough temporal spatial resolution time span, versus basic elements missing from the models, such as shifting jet streams or what? So how many cases of non or weakly attributable results are due to data issues? Well, I view this distinction between strong attribution results and non or weak attribution results. A lot of that has to do with the variable that you're looking at. So if you stick closer to temperature-related variables like global mean temperature or even regional temperatures, and you can look at extreme temperatures or look at the temperatures or the ocean temperatures increasing. Those are the cases where we're seeing the strongest evidence for attributable human influence. But if you look at other types of variables like, say, changes in the polar storm outbreaks over the U.S. during winter, things like that, circulation, things related to regional circulation features. For those, we have less confidence in an anthropogenic influence at this point. I think there's a distinction when one looks at essentially a lot of the different types of circulation and some of the storminess variables. The signal just isn't as strong in the data to begin with. And we also have lots of data issues, say when we're looking at hurricanes and trying to understand how many hurricanes there were, say back in the early 20th century. Well, that's a difficult problem. That's a difficult measurement problem because you needed to be just have a very extensive observation network to see all the storms, and to actually try to estimate their intensity, you need even better observation capabilities, better than what we had in place back at that time. So the part of it is our limitations in the measurements that we depend on to try to reconstruct the past. But part of it is, I think, is just due to the nature of the variable, that global warming. So we're adding this radiative forcing, positive radiative forcing to the planet, and it's warming up the planet. So to first order, that's the nature of the signal that we're seeing is a warming climate. Some of these other related features, like changes in storms and circulation, are sort of secondary features. They're coming along, but it's much more difficult to identify the anthropogenic influence in some of these alternative climate metrics that we see. I know that may be frustrating for some, but I think that's just the nature of the detection attribution at this stage. There was a question from Jerry Higginbotham. What was the reason for using the 1986 to 2015 versus 1901 to 1916 grouping for annual precipitation and temperature? I think there was a decision made in putting the report together that they wanted to use a common baseline for a lot of these climate change signals. So they decided, the report authors decided that they were going to use a 1901 to 1960 baseline to establish, and then they could show changes relative to that baseline. Now, actually, I showed some results in the talk which looked at linear trends, say, since 1901. So that linear trend approach uses all the data and really doesn't depend on a baseline. So that's a way of getting away from this whole issue of what baseline to use. Sometimes for my own work, I use 1881 to 1920 as a baseline for global temperature to see the rise of temperature out of that baseline. So there is some arbitrariness, I think, when one is choosing a baseline, whether it's 1881 to 1920 or 1901 to 1960. I think there's less arbitrariness when one is looking at, say, linear trend, which is why I focus on that a lot in the detection attribution work that I do. But I think regardless of whether we're showing this 1986 to 2015 versus the 1901 to 1960 baseline or looking at linear trend, I'm seeing very similar overall picture in these of the general warming with this lack of warming, say, in southeastern U.S. I'll go to the next question. Hunter Cutting. Regarding the long-term multi-decadal to centennial trends in TC activity and the accounting for past changes in observing capability, the CSSR report reported this is not meant to imply that no such increases have occurred, but rather that the data are not of a high enough quality to determine this with much confidence. In this light, why did you present a graphic and conclude there are no long-term trends? I think what we're concluding is that if there were a long-term trend, say in Atlantic hurricanes, I would expect to see some evidence for this, say, in U.S. landfalling hurricanes where we think we have a relatively complete record. So I think we have some reasons to conclude, at least at this point, that there's no long-term trend, no significant long-term trend, say, in basin-wide TC activity. But, for example, let's take the case of tropical cyclone intensity. Now, we didn't talk very much about detection and attribution of intensity changes in this talk. And part of the reason for that is that we don't have reliable global estimates of intensity going back very far, back, say, prior to around 1980. Now, if we lived in some ideal world and we had a perfect record of tropical cyclone intensities globally going back to 1900 and could actually do a trend analysis on it, we might in fact find some type of significant trend of intensity. But we don't have such a record that we can rely on. So that, I think, is that's what I think led to this statement that you're quoting from the Climate Science Special Report. We were especially had in mind, we were thinking about the issue of tropical cyclone intensities, or for that matter, tropical cyclone rainfall, where in fact there may be some influence of anthropogenic warming on tropical cyclone rainfall, but we just don't have the records of rainfall over all these ocean regions going back to 1900 that we can test to see whether we see such a change or not. So it really depends on the metric, but there are clearly a lot of metrics where we really wish we had data, reliable global data going back all the way back to 1900 or even before. We'd be in a lot better position to do this type of detection attribution analysis for those types of variables, but we don't have it at this point. I think there are possibilities of increasing our data record by using clever reconstruction techniques and even paleo data, but that's for another talk, I guess. Okay. I have one other from question. I think this may be my last question. So, as you presented in the CSSR, the authors reported that precipitation change for the continental United States, there's high confidence in the detection of extreme precipitation increases, while there's low confidence in attributing extreme precipitation changes purely to anthropogenic forcing. Why do you set the bar for discussion attribution that way purely? Why did the authors not report, for example, whether extreme precipitation can be attributed in part to anthropogenic forcing? Part of this is, as I showed some results for North America from some of Zubin Zong's paper, it depends a little bit. The results you get depends on exactly how you frame the analysis. And also this analysis was done for the North American region as a whole and not for the U.S., which was the continental U.S., which was the topic of the report. So I did consult with Zubin Zong, the author of that report, on what he thought we should conclude about precipitation extremes for our report. And I think Zubin was quite comfortable with the type of wording that we were using, being a bit more cautious. I think IPCC has a stronger statement to make regarding extreme precipitation, but they are making that statement from a global perspective, not a U.S. perspective. So we just don't have as many studies, quite frankly, that can get down to this regional level. One point that I neglected to mention in my presentation is that detection attribution at the regional scale is harder than it is at the global scale in general. It is for temperature, it is for precipitation and other variables. There's an advantage to being able to look globally. But this report was focused on the U.S. So we really didn't have a choice. We needed to try to say what we could about the U.S., even if the studies there weren't a lot of studies even focusing particularly on the U.S. So when you have that situation where you have studies focusing on other regions or regions that include the U.S. or global, and then you try to say, well, what does that mean for the U.S.? We have to make some kind of allowance as authors when we sort of make some derivative statement from some study. We sometimes have to put in a little bit more cautious words. Let's see if there was something else showing up. I think oh, actually, there are some more questions. Yeah. That's,
Sarah just had a comment, and so did Hunter, saying thank you.
Okay, just comments. Okay, well, I think that should wrap things up. So, again, thanks, everybody, for tuning in and all your interesting questions. And I hope you learned something today.
Yes, we did. Thanks so much, Tom. It's a difficult topic. And folks online, if you're interested in getting a video of this, we will be making a recording available. You can contact myself, tracy.gill@noaa.gov, or Katie Reeves, who is also on the emails, and we'll be happy to get it to you. It won't be right away, but maybe a day or two. Tom, thanks for taking the time, and I apologize for all the setup hiccups at the beginning.
Oh, no problem. Worked out okay. Thanks.
Thanks very much, everybody. I'll hope to see you next week for the next climate talk, the third in the series on July 26th, Droughts, Floods, and Wildfire by Michael Weiner from Lawrence Berkeley National Labs. Same time, and we will be using the same Adobe Connect setup. I hope I'll get on better and make it cleaner start for the presenters. So thanks again, Tom.
You're welcome.
All right, bye-bye, everybody.